For Ramanujan, mathematics is not brute force like a computer or savant churning digits. It has direction, selectivity, and relevance. It's targeted, elegant, and purposeful. He wasn't randomly generating patterns. He was choosing the right ones, like a sculptor chipping away at unnecessary marble. In this episode, we discuss how Ramanujan's mathematical genius, rooted in intuition and elegance, mirrors the principles behind Ramanujan graphs, structures that achieve near-perfect efficiency with minimal, purposeful connections. We'll explore how his selective, almost sculptural approach to mathematics informs these graphs, which balance sparsity with robust connectivity, and how this philosophy of choosing the right patterns applies to modern challenges, from optimizing networks to advancing quantum computing. Through vivid analogies and real-world applications, we'll uncover the beauty of targeted, elegant solutions in mathematics and beyond, inspired by Ramanujan's legacy.
Imagine designing a system, maybe the global internet, or even the busiest kitchen you can think of, and finding there's this hidden blueprint, a way to build it for almost absolute perfection.
How?
A network that's incredibly resilient, astonishingly efficient, spreads information faster than anything else, even with the fewest connections.
Right, that sounds almost impossible, doesn't it?
Exactly. It feels counterintuitive.
Our mission is to shortcut you to being well-informed about these remarkable structures, known as Ramanujan graphs.
Ramanujan graphs.
And we're going to unpack what makes them special, why they seem to defy our everyday logic, and how their surprising properties are actually revolutionizing fields, everything from quantum computing to optimizing that busy restaurant kitchen.
That's quite a range, and a diverse collection of sources.
We've looked at deep dives into the fundamental math of networks, explanations of cutting-edge quantum tech like adiabatic computing,
And even a concept for optimizing a national petrol distribution network. So get ready for some illuminating moments.
Let's start with the basics. Graphs. They're everywhere, quietly powering our interconnected world.
Hidden language of connections.
Exactly. They give this universal language to describe relationships. Think of them like maps, nodes, locations like people, devices, cities.
Edges are the links, the connections between them.
They model everything from your social network to the circuits inside your phone.
Here's where that paradox really kicks in. Common sense tells you more connections mean a stronger network, right?
Mm-hmm.
More roads, more traffic.
Seems logical.
Ramanujan graphs flip that idea. They are sparse, each node connected to only a few others.
Okay, sparse. Got it.
Yet somehow, they are extraordinarily well-connected and resistant to disruption. It's like building that city with minimal roads, but you can still get anywhere almost instantly, and no single road closure ever causes gridlock.
How is that possible?
That's the million-dollar question.
Well, that's the magic. The name itself is a clue. They're named after the legendary Indian mathematician Srinivasa Ramanujan.
Ramanujan.
His incredibly deep insights into number theory laid the groundwork for constructing these graphs. It's a beautiful case of pure math finding really powerful practical applications.
What makes a graph Ramanujan?
Our sources explain they're a special type of regular graph,
Regular.
meaning every single node has the same number of connections, like a perfectly balanced spiderweb where every junction point has precisely zero threads coming out of it. That consistency is the starting point.
Everyone's connected. Uniformity.
But the secret lies in what mathematicians call their spectral properties.
Spectral, like light or sound.
Think of it like this. Every network, based on how it's connected, has an underlying mathematical rhythm. We can capture this rhythm using a tool called the adjacency matrix.
Right. Maps who's connected to whom.
Exactly. And from that matrix, we can calculate these special numbers called eigenvalues. You can think of these eigenvalues as the network's inherent resonant frequencies, or vibrational modes.
They tell you how the network rings, vibrates, how signals move.
They tell us how efficiently information or influence or flows and echoes through the system.
This is where the perfection part comes in, with these frequencies.
This is it. For any well-balanced regular network, there's always one main dominant frequency, the rock. But for a graph to be called Ramanujan, all the other frequencies, the non-trivial ones, must be as small as possible.
The theoretical limit.
Exactly. The tightest possible bound, defined by something called the Elan-Bapana theorem. It's like finding a perfectly tuned musical instrument where all unwanted overtones, all the jarring noise, is minimized to the absolute physical limit. This isn't just good, it's provably the best you can achieve for that number of connections.
Wow, okay.
This perfect tuning, this specific spectral property, makes them optimal expanders.
Optimal expanders, what does that mean for us or a network designer?
In simple terms, it means they have incredible edge expansion and rapid mixing capabilities. This translates into networks with robust connectivity and incredibly fast information spread, even when using the absolute minimum number of connections per node. They are the ultimate example of network efficiency.
Okay, let's dig into these properties because they really do seem to defy common sense. This is where it gets interesting. First, you said they're sparse yet hard to fragment. Cost-efficient, only designate edges per node. But despite this minimalist design, they have this extraordinarily high edge expansion. What does that look like?
It means if you try to cut the graph into two parts, separating one group of nodes from another, you'll find a huge number of edges crossing that cut relative to the size of the smaller part.
You can't isolate a section.
It makes them almost impossible to break into pieces unless you remove a massive fraction of edges. This is invaluable for network resilience. Think of a lightweight bridge that can withstand a hurricane because its few connections are perfectly placed for strength.
Incredible.
Then there's their fascinating dual nature. They have this uniform local appearance, but globally, they have a small diameter.
What does that mean, uniform appearance?
If you zoom with an ocean graph, it basically looks like an infinite, perfectly regular tree or forest, just this endless repeating pattern of connections with no obvious landmarks or features.
Kind of disorienting, maybe.
Feel that way locally.
Yeah.
But here's the kicker. Globally, their diameter, the longest, shortest path between any two nodes, grows incredibly slowly, only logarithmically with the number of nodes.
Logarithmically. Even for a massive network, the farthest points are still relatively close.
You can get from any point A to any point B in remarkably few steps, even if the network has billions of nodes. Globally, everything is practically next door.
Being able to cross a huge continent in few quick hops, even if every town looks identical.
That's a great analogy. This leads to their next amazing property: rapid mixing of random walks.
Random walks, information spreading randomly.
Exactly. Or maybe a data packet bouncing around or someone exploring randomly. These random processes don't get stuck. They spread out and reach a uniform distribution across all the nodes quickly.
Information gets everywhere fast, no bottlenecks.
It makes them incredibly efficient for distributing data or broadcasting messages, and very resistant to certain targeted attacks or search strategies, because there are no obvious structural weaknesses or central points to exploit.
You mentioned an optimal spectral gap.
Yes, that's related to the eigenvalue property. The spectral gap is the difference between that largest eigenvalue and the next largest one in absolute value. Think of it as a measure of how well separated the main frequency is from the others.
Bigger gap is better.
A bigger gap is better. It indicates stronger connectivity, faster convergence, better expansion. Ramanujan graphs have the largest possible spectral gap for their degree dollar. This makes them supreme for efficient communication and flow within the network.
And underpinning all of this are these deep number theoretic roots.
Maybe the most surprising part for non-mathematicians. These graphs aren't just some clever combinatorial trick. Their existence, their explicit construction methods, come from deep abstract areas of pure mathematics.
Like what?
Things like modular forms, automorphic representations, the theory of quaternion algebras, Ihara zeta functions, connections to the vast Langlands program. It's this incredible intersection where pure abstract mathematical thought provides blueprints for highly optimized practical structures.
Pure math meets hardcore engineering.
You could say that. And this unique blend, sparseness, robustness, spectral perfection makes Ramanujan graphs incredibly valuable. We see applications popping up everywhere.
Network design and communications.
Building resilient, low-cost communication infrastructures. Designing peer-to-peer networks that balance load. Creating sensor networks that survive multiple node failures. You could imagine basing the next generation of the internet on these principles for efficiency and robustness.
Makes sense. You mentioned error-correcting codes.
Yes, they form the basis for a powerful class of codes called expander codes. These are vital for ensuring data integrity in demanding environments. Think satellite communications, data centers, long-term data archiving.
But cybersecurity.
Their structure, being so hard to decompose, is useful in strengthening cryptographic hash functions and pseudorandom number generators, making digital information safer.
In theoretical computer science.
Their use in de-randomization, making randomized algorithms deterministic, and for speeding up simulations like Markov chain Monte Carlo methods, saving computation time.
Okay, now what about the cutting-edge stuff? Quantum computing.
That's a really exciting area. There's potential for using them in advanced quantum error-correcting codes, protecting fragile quantum information. And they serve as ideal structures for running certain quantum algorithms, like quantum walks, which could be much faster than classical searches for some problems.
Machine learning, data science.
They provide stable structures for graph-based machine learning models like graph convolutional networks or GCNs. And they can improve techniques for visualizing high-dimensional data called spectral embeddings.
I wasn't expecting this one. Gaming and procedural generation.
They can create adaptive mazes in games that dynamically change while guaranteeing fairness, solvability, and preventing boring dead ends. Imagine a game world that feels endlessly fresh, but is never actually broken.
Generative music.
You can actually interpret the graph spectrum, its eigenvalues, as a kind of musical chord palette. Then you can use the graph structure to generate evolvingly harmonious soundscapes, music from pure math.
That's wild. Finally, social network analysis.
They can be used to model certain types of tightly knit communities that have strong internal connectivity despite not everyone knowing everyone else directly.
Yeah.
And they're great for simulating how information or influence might spread incredibly efficiently through such a network, even without dense all-to-all connections.
A huge range of applications. You mentioned quantum computing pushing boundaries. Let's zoom in on that. Quantum computing, or QC. What's the gist?
AQC. It's a particular approach to quantum computing that tries to solve really hard optimization problems. You start a quantum system in a simple, known lowest energy state, the ground state.
Okay, an easy starting point.
Then you slowly, adiabatically, change the system's parameters, morphing it from that simple starting setup into a final setup where the new ground state encodes the solution to the difficult problem.
Guiding the quantum system to the answer.
If you do it slowly enough, the quantum system tends to stay in its ground state throughout the process. So you just prepare the start, let it evolve slowly, and measure the final state to get your answer.
A classic hard problem for this is the max cut problem.
Exactly. Splitting nodes in a graph into two groups to maximize the connections between the groups. Sounds simple, but finding the best cut for a large graph is computationally brutal for classical computers. It's what we call NP-hard.
QC could tackle max cut. Where do Ramanujan graphs come in?
Researchers are exploring Ramanujan graphs as test beds for running QC algorithms, like max cut on those graphs.
Why are they ideal? What's special about running QC on a Ramanujan graph?
It leads to some really interesting ideas about how you design the quantum computation itself. Instead of just using a standard method to drive quantum evolution, they're experimenting with spectral modifications to the quantum program, the Hamiltonian.
Spectral modifications. Using those eigenvalues again.
One key idea is using a spectral filter driver. The part of the Hamiltonian that pushes the system isn't generic. It's constructed using the graph's own spectral data, its eigenvalues and eigenvectors.
The quantum evolution is tailored to the graph's structure.
Exactly. The initial quantum state is aligned with the graph's global modes, its main resonant frequencies.
And there was another idea, regularizer.
Something elegant called a spectral action regularizer, inspired by deep mathematics from Alain Kahn. We add an extra term to the Hamiltonian during evolution.
What does this term do?
Think of it as a spectral filter that helps to sculpt the energy landscape the quantum system is navigating. It can gently penalize undesirable quantum states, states that don't align well with the graph's good spectral properties, and amplify the favorable ones. It's like smoothing out the path to make it easier for the system to find and stay in that ground state solution.
Guiding the quantum system effectively.
Like a skilled potter shaping clay, or a composer fine-tuning an orchestra, you're using the graph's spectral nature to guide the quantum process.
Why are Ramanujan graphs the perfect place to test these ideas?
It boils down to their spectral perfection. Their non-trivial eigenvalues are as small as possible, tightly confined.
The quiet frequencies.
This means they have rigid global modes. There aren't many low-energy patterns available other than the ground state. This spectral cleanness allows those spectral filters and drivers to act more effectively.
Fewer frequencies to interfere.
Exactly. It leads to fewer problematic situations called avoided crossings, especially tiny ones. These are points during quantum evolution where the ground state energy level gets very close to an excited state level.
That's bad.
It's tricky. If the gap between energy levels becomes too small, the system can get kicked out of the ground state, ruining the computation. Ramanujan graphs, with their large spectral gaps and rigid structure, are expected to have fewer troublesome, tiny avoided crossings.
Making quantum computation more robust and faster?
That's the hypothesis. Comparing AQC performance on Ramanujan graph instances versus graphs that are bad expanders should highlight the benefits of these spectral engineering techniques. They're ideal for studying this approach.
Okay, this is leading somewhere profound, isn't it? What if we stop thinking about these optimization problems, just connecting dots or finding cuts?
What if we start seeing them as something deep, almost geometric?
This is where that huge conceptual leap comes in, the one inspired by Elaine Kahn.
The idea is to treat the optimization instance of the graph, the problem defined on it, as a finite, non-commutative geometry.
Non-commutative geometry, what does that mean in this context?
Think about the graph not just as points and lines, but in terms of algebraic structures. It's algebra of functions, the space it acts on, a Hilbert space, and mathematical operators like the graph Laplacian or a Dirac operator built from the adjacency matrix. It gives the finite graph a richer, almost geometric structure, but one where multiplication isn't necessarily commutative, hence mutative.
Applying tools from geometry to discrete networks.
The slow, gentle evolution of the adiabatic quantum computer isn't just about changing parameters in a Hamiltonian. It becomes something called spectral flow within this abstract, non-commutative geometry.
Spectral flow, frequencies are changing.
Yes, the eigenvalues are evolving. Kahn's powerful mathematical toolkit, like spectral action index theory, originally developed for understanding the geometry of space-time and particle physics, can potentially be applied here to analyze the AQC process, maybe even as a design principle.
How translate into actionable ideas for building better quantum computations?
One idea is using the spectral action as a Hamiltonian design principle. You could use functions of the geometric operators, like the Dirac operator, to sculpt the energy landscape, biasing the quantum path away from the problematic small avoided crossings.
Geometry design quantum program.
Another idea is using spectral flow or index theory as diagnostics. By monitoring how eigenvalues cross thresholds during evolution, you might predict or certify the robustness of the adiabatic process, how likely it is to succeed.
Like getting a warning if the computation is about to go off track.
Potentially, yes. There are deeper ideas about using operator algebras to classify different types of degeneracies or difficult points in the computation, leading to more robust ways to encode the problem.
The punchline.
The punchline is, this perspective shifts us from smoothly changing a quantum system between states to performing spectral engineering of a finite, non-commutative space. We're manipulating the fundamental geometric structure of the problem itself to find the solution.
That is a genuinely different way to think about computation. Mind-bending. Let's apply it to a concrete, real-world optimization problem.
Imagine this challenge. You're tasked with optimizing a national petrol distribution network.
Okay, for a big fuel company.
You need to do two things. First, choose a set of locations to build your main petrol depots. Second, you're allowed to open extra connections, maybe upgrade certain roads, build new pipelines between points in your existing network.
The goal is to minimize total cost.
Exactly. The total cost has two parts. There's the delivery cost. For every gas station or customer, calculate their demand times the shortest path distance to their nearest open depot in the newly upgraded graph. Sum that up.
Cost based on distance in the final network.
And then there's the edge opening cost. Just a fixed cost, beta, times the number of new road segments or connections you decided to build.
So you want cheap delivery, but adding roads costs money.
Precisely. That highlights the core tension. Classic example of two coupled, hard problems tangled together. Finding the best K-depot locations, like the K-median problem, depends on which roads are available.
And deciding which roads to upgrade, that's a network design problem, depends critically on where you've decided to put your depots.
The solution for one affects the other. They're interdependent, and both are NP-hard, meaning finding the perfect solution is computationally ferocious.
How do you tackle something like this? You probably can't find the perfect answer easily.
You typically rely on clever algorithms that aim for good solutions, even if not provably optimal. Our sources mention standard approaches, like the greedy K-median algorithm. Make a decent first guess at placing the depots based on demand and existing roads.
Okay, a starting point.
Use a greedy edge addition strategy. Iteratively add the new road connection that gives you the biggest immediate reduction in total delivery cost until you hit your budget.
Iterative improvement.
More sophisticated methods involve combined local search or simulated annealing. You start with a solution, depots plus roads, then randomly tweak it, slightly move a depot, swap an added road for a different one, and keep the changes if they improve the cost, sometimes even keeping slightly worse changes to avoid getting stuck.
Exploring the solution space.
This is where ideas related to Ramanujan graphs might subtly come back in. You could use spectral or Laplacian guidance.
How would that work using eigenvalues again?
For example, looking at the eigenvectors of the graph's Laplacian matrix, like the Fiedler vector, can help identify bottlenecks or natural clusters in the network. This might guide you to smarter places to put depots or add connections. Spectral clustering is another technique based on this.
Using the graph's frequencies to understand its structure.
Let's take that bigger conceptual leap with quantum computing. What if we think about this PetrelNet problem not just as connecting dots, but as an act of spectral engineering, inspired by the properties that make Ramanujan graphs so perfect?
How does that translate? Imagine designing the network like a Ramanujan graph.
Let's use that Ramanujan kitchen analogy. Think of it as a blueprint for operational perfection, where the layout and workflow embody the principles of a Ramanujan graph.
All right, the Ramanujan kitchen, let's break it down. Property 1, regularity, which you called essential adjacency.
Right. In the Ramanujan kitchen, every workstation, the grill, fryer, plating area, the pass has 3 essential immediate connections to other stations it interacts with most. No more, no less.
Discipline sparsity.
Yes, it enforces this radical idea that adding more connections isn't always better. More links can just create chaos, interference, too much traffic. Perfection here comes from the global pattern that emerges from these minimal, disciplined, local connections.
Okay, property 2, high edge expansion or resilience to chaos.
In this kitchen, it's almost impossible to isolate one team or section if something goes wrong. If the fry station gets overwhelmed, you can't cut it off easily. You'd have to block multiple routes simultaneously to disrupt the flow.
No point of failure.
There are always alternative, efficient routes built into the design. A cook from the grill needing something from pantry doesn't get stuck because the plating station is busy. The system inherently routes around bottlenecks.
Property 3, small diameter and fast mixing. Everything is close phenomenon.
If the head chef yells, 86 the salmon, that message gets everywhere almost instantly. The grill stops prepping it. Service knows not to sell it. Information and items like ingredients or finished plates travel with astonishing speed across the kitchen.
Preventing problems from cascading.
You don't get situations where one station runs out while another has excess, or where information fails to reach a critical point in time. Everything mixes and distributes efficiently because the minimal layout is perfectly interconnected.
Okay, last one. Looks like a tree. You called this decentralized excellence.
A new cook might feel lost because there's no obvious main street or central hub, like a central island that everything revolves around.
Is it good?
Because the absence of obvious landmarks prevents over-reliance on any single central point or person. It distributes the system's intelligence and workload. It also makes the design inherently scalable. You can add new stations or modules following the same connection rules, and the kitchen's core efficiency and resilience don't break down because it wasn't dependent on one overloaded center.
Decentralized, robust, scalable. Okay, I see the analogy. How do we fold these Ramanujan kitchen insights into solving the messy PetrelNet problem? What are the actionable ideas for you, the listener, if you were tackling this?
Okay, here's the crucial shift in thinking. When your algorithm is considering adding a new road segment, an edge in the PetrelNet problem, don't only evaluate its impact on immediate total costs.
What else should it look at?
Evaluate its impact on the graph's Ramanujanness. Ask, does adding this edge improve network structural quality in a way that mimics Ramanujan properties?
Like how?
Does adding this edge significantly increase the graph's spectral gap? Wider gap means better expansion, faster mixing, more resilience, closer to the Ramanujan ideal.
Reward edges that improve global connectivity, not just local cost.
Exactly. Does adding this edge move the graph's degree distribution closer to being regular? Does it reduce the variance, making nodes have more similar numbers of connections? This pushes towards that regular property.
You're not just optimizing cost, you're optimizing the quality of the network structure itself.
Precisely. You can create a hybrid objective function. Instead of just minimizing total cost, you minimize a function that balances total cost with a penalty for having a low spectral gap or a high degree variance.
The algorithm is explicitly rewarded for making moves that improve the graph's fundamental spectral and structural health.
You're guiding the search toward solutions built on a robust, efficient, well-engineered network foundation.
Doesn't it?
For instance, if your current network structure, maybe after adding some edges, has a nice large spectral gap, it's behaving like a Ramanujan graph. You could use a simpler, faster heuristic for depot placement. The network is already doing a lot of the work for you.
If the network has bottlenecks, a small spectral gap,
Then you know the underlying structure is poor. You might need a more sophisticated, spectrally guided placement strategy, like spectral clustering, to counteract that poor layout and ensure depots are placed effectively despite the network's flaws.
you could create a single Ramanujan score for any network configuration.
Absolutely. A score that combines measures like spectral gap, degree regularity, maybe even diameter. They use this score to guide your optimization search, favoring solutions that don't just have low cost, but also have a high Ramanujan score.
This brings us back to that crucial question.
Yes.
When designing or optimizing a complex real-world network,
Do you want to be the master chef who's constantly brilliant, but always fighting against a bad kitchen layout, putting out fires, dealing with bottlenecks?
or do you want to be the architect who understands the deeper principles, who engineers the very spectrum and structure of the network graph itself, designing operational perfection from the ground up?
The argument here is that the lowest cost, most resilient, most efficient solutions are found on networks beautifully connected, reflecting deeper principles of optimal structure.
Wow. What a deep dive. We started with this seemingly abstract mathematical curiosity, Ramanujan graphs.
We plunged right into their really counterintuitive perfection. We saw how their elegant, almost magical properties, sparsity plus connectivity, spectral purity, make them invaluable,
From high-tech fields like quantum computing, where they might unlock faster algorithms.
providing a blueprint for designing the ultimate efficient kitchen or the more robust national infrastructure.
Yeah. So for you, the listener, you now have a new lens, a new blueprint for thinking about optimal systems. It's not just about adding more resources or connections.
It's about finding that right balance, that perfect structure involving minimal connections arranged in the right way, driven by fundamental structural and spectral properties.
Leaves us with a final thought.
Consider the networks in your own life, your professional connections, maybe your team's workflow, the smart devices in your home, even your daily commute patterns.
What other seemingly abstract mathematical concepts, like the principles behind Ramanujan graphs, might be waiting to serve as blueprints for optimizing everyday systems?
How could we make them more resilient, more efficient, and truly beautifully connected? What hidden perfection are we yet to uncover in the fabric of the everyday?